There is a rule on every commercial flight in the world. Before takeoff and before landing, the window shades must be open, no exceptions. Flight attendants walk the cabin specifically to check this. If yours is closed, they will ask you to open it. Most passengers assume it is about the view, or maybe some minor procedural habit. It is neither. This rule exists because of specific disasters, because of people who died in situations where they did not have to. And when you understand what actually happened in those cabins, you will never close that shade again. Takeoff and landing account for roughly 4% of total flight time, yet they represent more than 50% of fatal accidents. That is not a coincidence. These are the phases where the aircraft is closest to the ground, operating at low speed with high thrust, and where there is almost no margin for error. In those windows of time, seconds matter, not minutes, seconds. And what happens inside the cabin during those seconds is just as important as what happens in the cockpit. The window shade rule sits exactly at that intersection. Consider what a modern wide-body airliner represents in terms of emergency challenge. An Airbus A380 can carry up to 853 passengers in an all-economy configuration. In the event of an emergency evacuation, aviation regulations require that every passenger must be able to exit the aircraft within 90 seconds. This is not a comfort target. It is a certification requirement under EASACS 25 and FAA FAR Part 25. The aircraft must demonstrate this capability with half its exits blocked, in darkness, with passengers carrying carry-on items. 90 seconds for 850 people. To achieve that, every second before an emergency even begins must be used productively. The window shade rule is part of that preparation, and the physics of what happens in a real crash make the reason brutally clear. The assumption most people carry is that this is a visibility rule for passengers, that the airline wants you to look outside and report something if you see smoke coming from the engine. That is partially true, but it is the smallest part of the answer. The real function operates on 3 separate layers, and understanding each one requires looking at actual accidents where the absence of this awareness led directly to preventable deaths. The window shade rule is not about what passengers see. It is about what crew can see, what rescuers can see, and how quickly the human eye adapts when it matters most. Flight attendants are positioned at their designated stations during takeoff and landing. They are trained to monitor the exterior environment. If an engine is on fire, if a gear leg fails to extend properly, if a wing strikes an obstacle, the first people likely to see this are not the pilots. The cockpit field of view is limited by design. It points forward. The cabin crew, seated facing forward or aft, depending on aircraft type, have lateral visibility through the windows adjacent to their stations. If those windows are covered, that information is lost. In the 1985 Manchester Airport fire, British Air Tours Flight 28M, a Boeing 737, suffered an engine fire on the left side during takeoff roll. The aircraft stopped on the runway. The left engine was burning. Passengers on the left side of the aircraft were seated next to windows. Some of those windows had shades that had not been properly positioned. Smoke filled the cabin within seconds. The evacuation became chaotic in the dark. 55 people died. The AAIB investigation noted that cabin situational awareness during the fire was critically compromised. Visibility, both inside and outside the aircraft, was a factor in the speed and effectiveness of the evacuation response. A AAIB report reference 8/88 British Air Tours, Flight 28M, Manchester Airport, 22nd August, 1985. When an aircraft comes to rest after an incident, emergency services arrive at a scene they have never seen before in that specific configuration. The aircraft may have departed from the runway. It may be at an unusual angle. Parts may be missing. What rescuers need immediately is an accurate understanding of where people are, where the exits are, and which areas of the fuselage are accessible. Open window shades serve as a rapid orientation tool. Firefighters and paramedics approaching a fuselage can see directly into the cabin. They can identify where passengers are seated, whether people are conscious, whether smoke or fire is advancing from a particular direction. Covered windows turn the fuselage into a sealed container. In every second spent by rescue personnel trying to understand what is inside is a second that the situation inside continues to deteriorate. This is not theoretical. It has been documented in multiple accident reports where rescue access process was delayed by the inability to assess interior conditions from the exterior. This is the layer that most people have never considered, and it is arguably the most important one in terms of direct physiological impact. The human eye requires time to adapt to darkness. Full dark adaptation takes approximately 20 to 30 minutes. Partial adaptation, enough to function in low light conditions, takes somewhere between 5 and 10 minutes. During a daytime flight, the cabin is typically bright. If a passenger has their shade closed, their eyes are adapted to the bright interior. Now consider what happens if that aircraft suffers a catastrophic event during landing. The lights go out. Smoke fills the cabin. The passenger must now navigate to an exit. Their eyes are not ready. They are starting the adaptation process from the worst possible starting point. As an open window shade during a daytime operation means that the passenger's visual system is already partially calibrated to exterior light conditions. If the interior suddenly goes dark, the transition is less extreme. At night, the rule inverts in its reasoning, but not in its outcome. Cabin lights are dimmed before landing for exactly this reason. If an evacuation occurs in a dark environment at night, passengers whose eyes are already adapted to low light will function more effectively in those first critical seconds. To understand why every fraction of a second in an evacuation matters, it is worth examining what the 90-second certification test actually involves. Manufacturers must demonstrate full evacuation capability before an aircraft type receives its airworthiness certificate. Under FAR Part 25.803 and the associated advisory circulars, the test is conducted with real volunteers in an actual aircraft, with half the exits blocked without prior announcement. Volunteers are not told which exits will be available. The test simulates realistic population distributions, including passengers of different ages and mobility levels. Lighting must meet minimum emergency illumination standards only. In real accidents, conditions are significantly worse than in certification tests. Smoke reduces visibility. Passengers are disoriented, and some exits may be jammed or unreachable due to structural deformation. The 90-second benchmark, designed to be achievable under controlled test conditions, becomes genuinely difficult in an actual emergency. Any delay introduced at the individual level, by confusion, by poor visibility, by eyes that cannot adjust to sudden darkness, compounds directly into outcomes at the aggregate level. The window shade rule eliminates one source of delay before the emergency begins. In August 2008, Spanair Flight 5022 crashed on takeoff from Madrid Barajas Airport. 154 people died. The aircraft, an MD-82, had a configuration warning system that failed to alert the crew that the flaps and slats were not set for takeoff. The aircraft rotated at insufficient speed and could not sustain flight. It struck terrain less than 2 kilometers from the runway threshold. In the wreckage analysis and survivor accounts, one of the recurring themes in the post-crash investigation was the speed of the sequence. From rotation attempt to ground impact was a matter of seconds. The survivors who exited were those who were positioned near working exits, alert, and able to act without hesitation in the immediate aftermath. Visual preparation, understanding of the environment, and physiological readiness are not soft factors in these scenarios. They are mechanical inputs to the outcome. CIA IAC Investigation Report. Reference IN-028/2008. The rule has limitations that are worth acknowledging. On flights where takeoff or landing occurs during complete darkness over open ocean or unpopulated terrain, the exterior visibility benefit for crew is reduced. The dark adaptation benefit still applies, and this is why cabin lights are dimmed during night approaches regardless of window shade position. In certain aircraft configurations, particularly those with smaller windows or window positions that do not align with crew stations, the direct crew observation benefit is reduced, and the rule cannot compensate for failures in other systems. It is one layer in a multi-layer safety architecture, but within its defined function, it operates reliably and at zero cost. There is no engineering solution required, no additional equipment, no maintenance schedule. As the window shade is already present, the rule simply ensures it is positioned correctly during the 2 phases of flight where it provides maximum value. So the next time a flight attendant walks past and asks you to open your window shade before takeoff, you now know exactly what that request represents. It is not about the view. It is not about regulatory habit. It is a calibrated safety layer that addresses crew situational awareness, external rescue orientation, and human physiology simultaneously. 3 distinct problems. 1 rule. The Manchester fire taught the industry about cabin visibility under fire conditions. The 90-second certification standard defines the evacuation physics. Dark adaptation science defines the physiological constraint. The window shade rule sits at the intersection of all 3. Aviation safety does not produce rules because they sound logical. It produces rules because something went wrong and people analyzed exactly how and why and then changed the procedure. Every rule that a flight attendant enforces has that history behind it. The window shade is no exception. And if you want to understand another rule that most passengers follow without knowing why, the tray table must be up and the seat must be upright for the same phases of flight. The engineering reason behind that one is just as specific and just as grounded in what actually happens to a human body in the first milliseconds of a crash sequence. I have covered that in another video.